My name is Valerii Kravchuk and I'm a principal support engineer at MariaDB Corporation. Today I'm going to speak about dynamic tracing on Linux as one of the ways to find and solve MySQL and MariaDB performance problems. I worked for MariaDB for more than 4 years. Before that I worked for Percona, Oracle, Sun, and MySQL. In general, I'm in this support engineer business for almost 16 years. I have my blog where historically I started to write about MySQL bugs mostly because in MySQL I worked in MySQL bug verification team and bugs were my main concern. I have a Twitter account called MySQL Bugs. I have a Facebook page that is to large extent used to be related to MySQL. So it's some social media presence. While recently I speak about all kinds of stuff related to MySQL and MariaDB, write blog posts there, kind of how-tos and everything. My bugs-related work was noted as well, and last year I got a MySQL Community Contributor of the Year award. What you should also know about my presentation that should be available online already is that whenever you see an underlined link there, you can just click on it and you will end up with some useful stuff. So I like my presentations to be used as a table of content or reference points. So based on my experience at work, I solve problems, and based on the time I work on all this, I know a lot of people and remember many things, how they happen. So as I put it, I drink and I know things. I should also say that while I'm working for MariaDB Corporation, I was not sent here, I'm not on a mission, and I'm representing only my own views and not the views of my current employer or any previous ones. I try to state only the facts I had verified myself, and I do my best to have correct statements, but please do not correlate my statements with any company policies for that matter. So, what is tracing basically? It's doing something when some event happens. Initially, it can be just as simple as printing something, like a debug print. It's the basic way to trace stuff. Profiling is in turn registering also some time or counters that related to the events happening. So historically, there are many ways to get tracing and profiling information in MySQL and MariaDB. Developers used to like to work with so-called debug binaries that, among other things, provide a way to trace the entry and exit from each and every function in MySQL code, for example. So via debug package, and all these printouts, all this tracing can be dynamically enabled and disabled in debug binaries. Thing is, nobody runs debug binaries in production because of performance impact. That's why developers used to require repeatable test cases and so that they can work on them with debug binaries. If you're a MySQL DBA, you also have a lot of tools to understand what's going on inside your server. You mostly should care about SQL queries that take a lot of time to execute, and for this you have slow query logs. There are different performance counters that are available via show global status. For specific storage engines like InnoDB, you may have extended details on internal workings of the engine, both total counters and per second information that is already a kind of profiling. So some of this information appears and goes away. For example, show engine in InnoDB mutexes that provided details about weights on mutexes is already gone starting from MySQL 5.6.14 as far as I remember. It will be gone in MariaDB 10.6 as well entirely. Additional way to get insights are added with time. In MySQL 5.0, we had information schema added mostly as a data dictionary representation. But later, there was a useful framework to add plugins that may present things in information schema, and a lot of useful tracing and performance-related information, for example, log weights in case of InnoDB, were added to information schema. Some users of MySQL and forks of MySQL added other details. For example, user stat was added with details of number of operations executed per user, per specific client, per specific table or specific index in the form of user stat. It's again a separate database. Percona server for MySQL and MariaDB server, for example, incorporates user stat, and you can enable it and use it. MySQL 5.0 also added one of the main community contributions to MySQL show profiles that was added by Jeremy Cole. So with this, you can split query execution into stages and write down how much time was spent at each stage of query execution. So it's already a bit more detailed than just logging slow queries. In MySQL 5.5, the performance schema was added, and it's a key point. It had not only added more details like weights per stages, but it's the idea how to collect information changed. The information is collected in memory buffers, ring memory buffers that are overwritten when overflown. So the idea is to have as lightweight profiling and tracing as possible. And performance schema is also a database, so you, MySQL DBA, can run queries against table there. And if you care enough to save this information into real tables, you can even join them efficiently and come to a lot of conclusions. So performance schema is cool and quite similar in some regards, like using ring memory buffers to other dynamic tracing techniques. It's evolving with every version, and there are recent changes and additions in MariaDB 10.5 that make it more or less similar to MySQL 5.7 with regard to performance schema. From the other side, you can just capture packets on the wire with TCP dump. Those go into MySQL server and back. There is timing information there, there is all the payload, and you can see the queries and how much time was spent by the server. So it's like yet another way to implement slow query log and understand how much time it took server to reply to the query. It's a popular way to analyze the traffic. What I advocate here in this talk and in general for more than 4 years is to use operating system level tracing and profiling tools. Thing is, MySQL is not the only software that needs profiling. Linux kernel itself needs profiling, and it does a lot more than just MySQL. So my main idea is that if some profiling technique is good enough for the kernel itself, it should be good enough for any process. And among the tools already available in the operating system level, we may have real-life profilers like perf, poor man profilers like PTPMP, tools to do all kinds of stuff. And I'm going to speak about these tools. Not all of them, but 3 main ones. So this session is mostly about tracing and profiling MySQL and MariaDB server. But basically, I advocate to use the same approach as for tracing and profiling any other process or kernel itself. This is specifically important in production, and I will say why. And of all the tools that provide some visibility to what's happening inside Linux, I will be mostly interested in 3 main set of tools that started to appear more than 10 years ago. Historically, the first of them is so-called ftrace function trace interface. That is that was created by Linux kernel developers based on some stuff introduced by GNU profiler. So it introduced some code at the beginning and the end of the function for profiling. And this idea was then used in a nice and hackish way, so that one can add the tracing when it's needed and disable it when it's not needed without changing the code. The code is changed on the fly. So the ftrace is the basic interface available for a long time. Soon after that, it was extended to have access to performance counters, and a command line utility and profiler, sampling profiler itself, perf, was added, and this is what I'm going to use for the most part of this presentation because it's widely available. And even later, to reduce the impact of processing and collecting the information. so that it can be processed at kernel context, aggregated as much as possible, and written to user space only those details that are needed. So for this, Linux kernel developers extended the idea of packet tracing from a Borland packet filter that was initially used also for TCP dump, I already mentioned. So the idea was to have a virtual machine that is executed in kernel context, and you write programs for this machine that are executed again in server in kernel context, and this is what ended up as extended BPF, eBPF. And there are tools, BPF compiler collection tools, and command line tools and utility with a simple language similar to AWK called BPF trace. So these three tools, sorry. I discuss dynamic tracing approaches, so without the need to add anything to the code, using these tools and problems I hit in the process of trying to apply them. But before we continue, the main idea is to have as little performance impact as possible from all the tracing and profiling. You can add debug printout, so use debug binaries, but it would be too slow. So before I continue, I would like to say a few words why I'm not concentrating on using performance schema, that kind of a profiling utility inside MySQL itself. Most important reasons are the following. First of all, it may be not there. It may be not enabled or maybe not compiled in, depending on the fork of MySQL you use. In MariaDB, it's not enabled by default. So I may not be even able to use it unless I restart. I may not be use it efficiently unless I restart, because performance schema is not dynamic enough. As I found out hard way many years ago, while working on this specific MySQL bug, some instruments in performance schema can be enabled only at startup, and it's not even documented in details which of them should be enabled only at startup. So the instruments you need may not be there. Sizing the memory buffers is a problem. So it's less of a problem recently. Some of them are dynamic, but historically you had to put the size, and it's overwritten, and you may lose the important information you collect. Another reason from my experience that not entire code is properly instrumented, unfortunately. So you may not have the instrument you need, you may not have the stage you're interested in. The plugin you use, for example, Galera, replication is important with MariaDB. It was not instrumented 4 years ago, and it's still work in progress to instrument it properly in performance scheme. The most important, though, is this thing. Whenever you work on performance problems, you have to approach it from both sides, from your software side and from the operating side and from the operating system side. So you need to know how much memory is used. You need to know if any disk I/O weights are involved and all that stuff. And for this, you have to track it from the operating system as well. So if you profile the operating system using perf, for example, and profile some other way for MySQL-D binary, how do you put and compare this information together? It's complicated. So my main idea was to use the same efficient approach, both for the client software, both for MySQL and for the kernel and for all libraries and for everything, as kind Linux kernel developers allowed us to do. Also, it's important in my specific cases, it's my own problems mostly, that I do not like to write huge SQL queries that may be needed to get the information from performance schema, and that MariaDB developers prefer to get stack traces, profiles and everything, and not performance schema outputs. Their stack traces are more convenient, so they're thinking about MariaDB in terms of their functions, not performance schema instruments that are not matching each other 100%. So what do I suggest? I suggest to use modern Linux tracing tools that cover the entire application stack, from the user processes to performance counters at processors, applications, libraries, all kernel components, device drivers, and everything. Of these, I already named. I am interested in ftrace, perf, and BPF trace mostly. There were previous tools of this kind like System Tab, but they are already gone, so I suggest to use more than once. And as a reference, you can use a website of Brendan Gregg and his good book specifically on BPF recently, and his site and his blog covers all this stuff. You can see diagram that I borrowed from his blog showing which tools you may use on Linux to look at which specific parts. So we can use perf to look everything. That's my main point. But before we start to add dynamic probes and everything, we need to understand, okay, tracing is doing something when some event happens, but what kinds of events are actually exist? We should better classify them. And I suggest to classify them by two dimensions. One dimension is the event in kernel, and other dimension or event in MySQL in user space program. That's one dimension. Other dimension is, should we do anything in the code to generate the tracing event? Like with debug binaries and debug package, you have to put specific calls or macros into the code. That same happened to so-called dtrace static probes, initially introduced by dtrace tool originating from Solaris and now available on Linux as well, on Oracle Linux at least. So if you have to do something in the code, it's manual annotation. So they come in the form of kernel trace points or user land statically defined trace points or dtrace probes. These are less interesting to me. More interesting to me are those automatic events that can be added on the fly to the kernel. It would be a kernel probe, or to the user space. It would be a user probe. So that's my main point of interest here. And specifically, I'm interested in user probes. So with this in mind, one would imagine that as we speak about Linux and it's a kind of Unix operating system, whenever we need to get some information, we have to work with some files and directories. So indeed, when kernel developers added dynamic tracing facilities, they added a special file system, tracefs. It's a type of file system that can be mounted somewhere at prods or sys or whenever you prefer. When you do that, you get access to some directories and files. These are text files, so you can write something there to add the probe, for example, enable tracing, and you can read from some other files to get the result of your tracing. This is a basic mechanism as it was created and covered by so-called ftrace. Stays for function trace. So basically, initially, the idea was that you can add probe to the beginning, entry to the function, and at the end, return from the function. Then on top of this, access to performance counters and performance events were added. And on top of that, a real-life useful sampling profiler called perf was created. And this is what we will mostly use with MySQL and inside this presentation. It's the most widely used tool for dynamic tracing. Then when eBPF was added to kernel, a lightweight virtual machine was added that could execute some aggregation code inside the kernel, inside the probe, not in the user land. To access this virtual machine, a set of compilers were created and a collection of tools called BCC BPF trace compiler collection tools and programs based on them were added. They also work with the same ftrace mechanisms mostly, or via the performance counters that are already available. But they provide a different way to access them, a front end. So these tools may be written in C, may be written in Python, maybe in other languages. So you write Python programs, they are compiled into a virtual machine code. This code is executed as something to do when something happens. So instead of just printing something, you can do a lot of more advanced stuff. You can program almost anything. The last but not the least, recently quite efficient command line tool implementing a simple language like AWK pattern matching and simple actions called BPF trace was also added. It's again a front end. The base counters, the base memory areas, ring buffers, maps, and everything, they are still provided by the kernel in the same form that ftrace largely used, but you can access it from different point of view. So basically, how you use ftrace directly, you have to mount tracefs. Usually it's mounted on syskernel tracing, and then you will see a set of files and directories there. When you are adding user probe, for example, you will see something written to the file called syskernel tracing uprobe event. Rarely you work with this directly, but if you want, you can do that. There is a problem. Ftrace is low-level interface, so you need to know, for example, which is the address of the function inside the binary. You can get this information with objdump. For example, for dispatch command, it would be this specific address. In, as far as I remember, it was MariaDB 10.56. So it may change with version and fork, surely. You need to know, if you care to print something like arguments to function call, you need to know how they are passed at the low level in your specific processor architecture. So in my case, for example, I was interested in the query string. So I want to capture all the queries that user sent to MariaDB and print the text. So I know that query in this specific version is passed as the third argument. It's a string. And I know that on Intel, this argument is available via DX pseudo registry. And there is some trickery also there that you should either find out by experiment or pick up from perf. Created dynamic trace point. So how it works? You add a trace point, user probe, sorry, in this case. P, it's a probe, you give it a name after a colon. You say that it's a probe for this specific binary at this specific address, and you can stop at this stage. Or you can continue and say that I would like to give a name query to the argument passed via this register, and I would like to print it as a 0 terminating string. You write this to uprobe events, you can overwrite it or you can append to it. So you may have many events traced. Then you enable this specific probe, then you enable tracing in general. And then when you want to read collected information, you just read from one of the files. Each file is representing the information differently. Trace pipe will represent it as such. The name of the binary, the process ID, which CPU we noted this specific probe running on, time since we start tracing in microseconds, name of the probe, address of the probe, and our argument and its value. So we captured real queries this way. It works on all Linuxes 10 or 11 years old, starting from 2.6.27 kernel. In any CentOS you can find, CentOS 6 you can find in a while, not on 5. For the details, go follow the links. What is clear from the above? That first of all, you need root access or sudo access for specific commands. Otherwise, you will not be able to run these commands. And dynamic tracing in general, all forms of it requires root or sudo access. These are the main problems to enter this way, because DBAs may not have it, but it's not the most serious problem, and eventually it can be resolved. So I shown you how you can find the probe address. It can get way more complex when you have complex programs written in C++ with virtual methods, class methods. Some hints are here. And you may use perf to find out real addresses and then just use ftrace directly if there is a problem. If the arguments are passed are not simple strings but some complicated structures, you need to find out how actually to get to the structure element that you're interested in. It's not obvious in some cases, but it's about offsets mostly, or passing through registers or whatever, accessing addresses. And it's error-prone, surely. If you need to trace the return from the function, you just replace P with R in the probe. And when you are done with the probe, and there are many other probes, you can just remove it by passing minus and probe name, and it will be removed. So that's it, a lot of extra reading. I would say that ftrace is not that easy to use directly. So whenever you see you have a chance to install perf package, it's additional package, it may not be installed. You should install it. And perf is a sampling profiler, which is a cool tool by itself. We will use it mostly for adding dynamic probes, but as a profiler as well. It has a lot of commands. Perf without arguments will show you most of them. We are mostly interested in 5 commands. Perf record to record profiling information or whatever. Perf probe to add or remove probes dynamically. Perf report is a way to process recorded information in and present it in different ways. Perf script is a way to dump the recorded information as is. And finally, perf top is a nice interactive utility that allows you to see at real time where the time is mostly spent, dig into the code up to the assembler level and see up to a specific instruction where the time is spent. It's also really cool. So use perf whenever you see it. If you do not have it installed, install it. Let's consider yet another example. Along the lines of the previous one with ftrace, I would like to capture the SQL statements, but this time I'll do it in MariaDB 10.5 with perf. So to add the probe, you just have to use perf probe -x. Then after -x, you have to specify a full path name to the binary. So it will be a probe for this specific binary. Instead of hexadecimal address, you just say, I need a probe for this function. It would be at the enter of the function. And I would like to print this specific function argument called by name. So perf knows names if they are present. It can resolve them as a string. Again, 0 terminating string. Then you can record everything. You refer to a probe name, and then you can process and dump the raw content with perf script. You can see what probe is created in ftrace. When you are done, you can delete it. So the output will look something like that. You can control output format with a syntax like print, for example, but basically you see similar information, binary name, process ID, which process this probe was running on, microseconds since we start tracing when something was executed. So if you check in between, you can measure, or if you check, for example, create one probe to enter into the function and another probe to exit from the function, return probe, you can measure how much time exactly was spent inside the function based on dynamic probes. So perf is easier to use. The summary is here, but let me show you some real life example if time permits. Let me double check. Okay, probably we can. So I have done this here in a couple of other windows. Sorry for the delay. On Ubuntu 16 with latest and greatest Percona server for MySQL 5.7. So what I did. First of all, I need to understand what to print and which version and build is different. To find out where in the code is what I need, I actually attached GDB. I had to wait for quite some time. Then I went to the dispatch command. I know this is where I can find the information I may eventually need. Just for the reference, I disassembled dispatch command to show you how it starts. Later, I will show you that the code is changed on the fly. So then after that, I had found out, it was probably here, in a bit hard way, that, no, not here, but earlier. So in an earlier session, I had found out the following, that the actual, let me see. Oh, yes, here is the actual session. So I set a breakpoint at dispatch command, and when I hit that breakpoint, I was looking for the SQL statement. So I checked that there is a com data argument that is a pointer to a structure, and this structure has the com query member that has is a union, and we can see a query here, or just another structure. So here it is. Basically, I have to print com data pointer com query dot query to get the query text. So this was the information I've got from GDB or source code review. And then when I decided to add a dynamic probe, I did it in the following way. So I've added the probe with this command. Then I recorded for some time. Now I'll record for just 20 seconds. Then I connected from another program, from another terminal, and executed some commands. For example, and I will see if my probe had ever executed in the process. Okay, it was too late already, but I executed some commands. Something was written, 11 samples. Let me see what is there. For this, I will use perf script, and then we can see what is in queries. Here it is. So we captured all the queries that were executed against the table when we connected. We have select version here, we have select 1+2 here, and all this information is truly here. What's more important is that actually when I started to collect the probe, I attached GDB again, and when I disassembled the same command, I've seen this debug interrupt added. And the code had changed to call the probe text. So that's really the magic that happens behind the scenes. And when I'm done with this probe, I have to remove the probe as it's stated on the slide. So let's move back to the slide. It's a real thing, it depends. In other case, with all the MariaDB on Fedora, while trying to do the same, I hit the problem that I was not able to add the similar probe. I had not studied why is it so. But I tried to add some other probe. I probed a bit higher level command do command, tried to find out how to get the query text there. And there is a local variable called packet, but it's not available at the entry. You can get errors. It's somewhere, it's copied from somewhere inside the thread structure, but I was not able to access so deep structure member. So I had to dig out what to do. There is an option called vars that show you which variables you can access in the probe actually, but it had not helped as I was not able to deal with thread easily. There is another option called line, which is quite important. Thing is, you can add dynamic probe not only to the entry and exit from the function, but almost to every line of the code, to every other line of the code, every executable line of the code. It just will be a different offset. So with line option, perf shows you what you can really trace. And here you can see the code, and that this is a debug printout at the beginning of the function. And eventually I found out the line 157. It's like from the beginning, where I see that we already fetching local variable packet from the thread. So what I did next? Next, I did the following. I tried to add the probe not to the entry of the function, but to the specific line in this function. So the offset was calculated, and there I printed this, the packet as a 0 terminating string, and it worked in the same way. While it was just an exercise caused by the problem with specific version of MariaDB, it proved this. I basically can add dynamic probe to every other line of the code of any MySQL or MariaDB function. It's not what Performance Schema already did, and maybe in upcoming 10 years it will not happen with Performance Schema, just because it's a lot of work to do really to trace all this stuff. So it's the most cool thing. I can do the same to any library, I can do the same to the source code of the kernel, but let's move on and proceed with that. What else you can do with perf? You can surely add probes to the kernel trace points so that you can trace, for example, block IO. specifically, you need to find out the probe name, and you can trace the stuff, and you can find the details here. Now, what else? You can add probes not only to MySQL or MariaDB, but you can add probes to the, sorry about this, looks like something disappeared. 1 second. You can add probes to any library. This is what I did to trace malloc calls. So I added a probe to the library implementing malloc and printed the size of the memory allocated. So I was able to print allocations of memory dynamically. And here is the blog post explaining that. This is a real life use case when one of MariaDB developers asked me how we can do dynamic tracing of specific function in specific storage engine. He wanted to verify what records in range is returned for memory tables. So I was able to do that as well. The trick here is to work with C++ members, and it's described in the blog post. I also hit a problem that if you have a virtual class member function in C++, it's not easily traceable. I had not found a way to trace it. Another real life use case. So mutex wait. I've just got a question. Can we apply dynamic traces to trace the mutexes? Yes, we can. I was tracing pthread mutex log, and there is a blog post about that. So perf can be also used as a profiler, and basic use cases that is already quite popular among my customers and was used for many real life performance problem solving cases is this. You just record samples with perf record. Now with stack traces, that's why a G argument. On all CPUs, that's why -A argument. You can trace forever or for specific time with sleep, as I did, or until you kill the process. And then you can process this information with perf report. And in perf report, if it was collected with -G at specific frequency, you can see how many samples, percentage of samples with specific stack traces in during the entire process of execution. So here is an example that got me converted to perf instead of performance schema once and forever. This example is a real-life use case from 2016, where in a complex high-loaded Galera cluster on one of the nodes that executed a lot of updates, simple selects by primary key, single row by primary key, sometimes spent 10 seconds, 15 seconds, 30 seconds doing something on the high load while updates proceeded. So why these selects were slow? I tried all kind of tricks with performance schema. It showed me that the time is spent at statistics stage. What statistics may need, it's like a part of optimization to get statistics. What statistics may really need, the query select one row by primary key. Thing is, in InnoDB, it still dives into the index structure to find out how many records are estimated per key, even though the answer is known beforehand, it's at most one. But it did so. And unfortunately, in that case, customer had limited the concurrency inside InnoDB, so to 32, for example. So when there were 32 updates doing a lot of work, all 32 InnoDB threads were busy, and the select had to wait in QE. It was not visible in performance schema because this is not documented. I reported bugs about all this stuff, but it was clearly visible in perf record. So we see, we at statistics stage, we read the tables inside optimize, so read it that way. And we were reading from InnoDB, and we were waiting most of the time, 71% of the time, to enter the InnoDB queue. So we just removed this artificial concurrency limit, and the problem was resolved. Even though before that I was studying Galera, multiple nodes interaction, all that other stuff. So is perf a universal answer? No, perf also has some problems to deal with. Basically, there are two problems. First of all, the amount of information written by perf, for example, over 60 seconds, may be huge. When we traced just everything in IO bound case, it was like 33 megabytes. it was already IO bound. So writing down 33 megabytes to perf data file is quite a law that influence the IO bound case. So what is the answer for this problem? The answer is to summarize the information and process it while in memory and in the kernel context. The answer is basically eBPF, extended BPF. And perf output with stack traces is too huge to work with, so we need some way to summarize it, maybe similar to PTPMP, or visualize it. And here we have a nice answer in the form of heat maps of lame graphs. So when we can graphically represent somehow. So these are the remaining topics of this presentation. eBPF, I already explained you how it works, but basically we have a LLVM virtual machine in kernel context that can execute a BPF code. BPF code is generated from your probe by the compiler. It's verified. It's verified that it does not have loops, that it's correct, that it never crashes, and it's a big deal. System tab allows you to create a kernel module for tracing, but that kernel module can do everything and crash at any moment. Here we know that the BPF program, we verify it, that it will complete. And if it cannot complete or do something incorrect, we do not run it. We return error. When we run the program, it has access to all kinds of probes, trace points, performance events, CPU, and everything. It puts the information into the ring memory buffers called maps, and then you can just collect aggregated statistics to the user land. So only aggregated data are stored on disk, for example. So you can follow Brendan Bragg surely for this topic as well as for everything else related to dynamic tracing. You can follow Julia Evans' explanations of how it works, but basically this I've already explained how it works. Pre-processed data are exported to user space, not the raw data. And you can use all the power of programming language to process them, not just text processing tools at Linux level. eBPF was evolving at kernels 4.x, and to use eBPF efficiently, you ideally need kernel 5 point something, like recent Fedora, Red Hat 8 or whatever, not my Ubuntu 16, for example. That's why I do not present the examples. And you use eBPF either by some BCC front-end program already created, or you create a new one, or use BPF trace. Of the existing BCC tools already created that you can just run, one of the important is TP-list. TP-list lists the trace probes in the binary, and you can find out hardware that, for example, MariaDB on Fedora package have the trace probes. MariaDB packages from MariaDB Corporation or Foundation do not have them, and you cannot find them in the code of MySQL 8 entire. There is a tool to add dynamic user probes, and it's called trace. Again, I did the same exercise with ftrace and with perf. I captured the statements executed. The syntax is a bit different. We have to use mangled command name. We have to provide the format as in print, and we can use function arguments by the name argument 1, argument 2, argument 3. There is a blog post with a lot of details explaining how I did it. The last, there are many more tools. I will just not concentrate on them that much. The last topic for today's talk is BPF trace. So BPF trace allows you to create simple scripts, not Python programs, but they are equally powerful. It's a front end to eBPF, and it guarantees, the syntax itself guarantees that you cannot program something that is absolutely incorrect and will be refused by the virtual machine. So how BPF trace works? There are different command line options, not that many. -L lists trace point that matches the template. -E just execute the trace point, and in general, they execute the probe. The syntax of what is executed, you may have multiple -E options, so execute many things. The syntax is simple. So you have a probe or list of probes separated by commas. You have an optional filter, so apply only if something is true, and you have action in the curly brackets, like here. The probe is kernel trace point syscalls sys enter open, it's file opening. The action, there is no filter. The action is printf, literally like in AWK. The command name and argument called file name printed as a string. It really resembles me AWK. That is my favorite programming language in Unix. So I just follow Brandon Gregg and I claim that BPF trace is cool and it's a future. Because among other things that were already presented, it also provides a useful built-in functions. For example, uStack will provide you a call stack. Kernel stack, key stack will provide you a kernel stack at the same moment. And these stacks can be formatted differently like perf or own format. So when we format them like perf, we can use these in all tools that accept perf input. You can use BPF trace as real profiler because there is a profile probe that just sample at given frequency. So here I've captured stack traces like poor man perf. And here's what I've got. There is a blog post explaining a lot of details. So what is the point? The point is the impact and performance of the resulting solution. For this, on this slide, I implemented a simple test. So I captured PTPMP outputs once per second for 60 seconds, perf samples 99 times per second for 60 seconds, and BPF trace profile. And here the difference in dropping down in QPS for specific sysbench test. So you can see that eBPF allows you to have a neglectable drop in performance, unlike PTPMP, and notably smaller than perf, just because we collect less information at user left. Flame graphs. So all these stack traces you can collapse and represent differently. I will not go into much details here because of lack of time, but you can graphically represent the amount of samples or amount of time spent at specific calls. This is this SVG file that is generated that way should be opened in browser, and there you can see all the details. You can dig into specific lines of the code and everything. Here there is also an example where I had used the pre-existing BCC program of CPU time, because it's not so easy to track when you get out of CPU. There are many conditions for this. So to summarize, what are the problems with this approach? You need sudo access or root. There is a problem of debugging the program that is traced. I had shown you that by example, that because the code is changed on the fly, debugger can be misguided and does not work as expected. There is still a problem of adding efficient probes so that not too much memory are allocated. So it's a common problem with performance schema. There are some problems that I just do not know how to resolve myself, like how to add the BPF trace probe to somewhere inside the function, but we can always do it with perf. There is a problem of access to symbolic information. The software should be compiled with no mid-frame pointer. In case of MySQL or MariaDB, we need debugging for packages. In some cases, we may have more tools to install, but this is a resolvable problem. First, in simple cases, we can rely on ftrace. In more complex cases, there are technologies developed mostly in Facebook, so-called BPF type format, and compile once, run everywhere as a way to efficiently embed the type information and symbolic information into the program that should be available only where the program is created, but then you can run it. Same as BPF trace, it would be the first binary that is affected by this stuff. So the last but not the least, there is some lack of knowledge and practical experience with these tools. That's why I'm promoting them. But of them all, GDB and perf are already standard tools for my customers specifically. I am yet to use the plenty of eBPF tools, and I am yet to study the details of ftrace usage. I will blog about it, write about it, and share my knowledge. Do the same, please. Thank you very much for your attention, and thank you, Shiv Iyer, for organizing this conference. Bye.
Valerii, welcome to MinervaDB Athena 2020. Great to have you here for this conference. Thanks for registration and talking.
Thank you. Thank you for your efforts to organize this great event.
Thanks for support, Valerii. The conference becomes great with great speakers like you, committee members, sponsors, and attendees. So it's a collaborative effort on behalf of MinervaDB Athena team. I take this opportunity to thank you. Your topic is one of the most interesting one for the conference. I tell you why. Because when it comes to MySQL troubleshooting or MariaDB infrastructure operation troubleshooting, native tools are definitely the first immediate pick for most of the database architects or database administrators. But you have come up with a unconventional set of tools like BPF and dtrace. These are outside MariaDB ecosystem. So can you share with us like how these tools are going to complement already existing utilities provided by MariaDB and MySQL, also for Percona toolkits?
Okay. So yes, indeed, MySQL DBAs have at their disposal a lot of tools to get some insights on what happens inside the server, where the time is spent, what are the weights. And since the introduction of Performance Schema, with each major release of MySQL, and recently MariaDB made a big step in this regard in 10.5, so we have more and more insights. What we miss and what we usually need is to check the load from the hosting operating system side. So you still need to care. You need to run PS, check for free memory, check disk IO load, and whatever. So even if you use native tools for the database, it's not the only source of information. Now, the main host operating system for current large-scale and production installations of MySQL or MariaDB is Linux. The performance problems on Linux are not inherent only to database servers or to MySQL. So there are many of them to be resolved and successfully resolved in the kernel itself. At some stage, some 11 years ago, the developers of Linux kernel decided that they need dynamic tracing capabilities so that they can get the insights into specific parts of the kernel code they need, and they can do it at the moment when the problem happens, so dynamically. They built this framework, and I explained the stages of building it. eBPF2, for example, is just the latest stage with a separate virtual machine inside the kernel that allows you to program your data collection and aggregation up to endless complexity. And dtrace specifically is like the first implementation of such ideas initially in Solaris. So we have this at our disposal, and we have a need, I assume, to check some system level metrics, also dynamic. The idea behind the approach I advocate is to use the same tools, dynamic tracing tools, to trace, among other things, MySQL D as yet another process. We have access to the source code. We know all the code internally. We know what function names mean. So as long as we can get traces of when the functions are executed, what they return back, how often they are executed, how much time is spent, and all this we can get for any process, including MySQL D from the dynamic tracing, we get a unified system that provides the insights, both to the operating system resource usage, to other processes. If you care, maybe you have application server running on the same system. The system that can be applied to containers, to C groups as well. So system that is already built by others in Linux world for the real life scaling applications. We just apply these tools when needed and get the same kind of details, the same level of dynamic output. We can include kernel stacks along with application stacks into a single output, fold them, analyze them. And that's all with the same approach of dynamic tracing on Linux. So that's what we can. You can still, and you have to still understand how the queries are executed, what are the query plans, and you still use all the show statements. But whenever you need to understand the impact of the outside components on MySQL, or is it impacting the entire system, then dynamic tracing is your friend. It's also your friend just because you can instrument basically every other line of the code dynamically without the need for anyone, MySQL developers or MariaDB developers, to put any line of code inside to get it instrumented. This should happen. This is happening right now. but you may miss that specific point, while dynamic tracing allows you to put your trace statements there and do it in the least intrusive way. So that's
Understood. Understood. So if I correctly understand you, if I'm a full stack performance optimization guy at a production scale, if I combine dynamic tracing probes with the native MySQL MariaDB tools, gives me an effective cockpit view of the entire performance bottleneck happening within MySQL and even outside MySQL.
Yes.
Right? Did I understand?
Exactly. You will get your familiar details in your familiar way via your familiar SQL statements for MySQL, but you will get, again, the familiar level of details with system-wide statements and commands like perf profile for the entire stack of applications running on your host operating system. And by comparing, by correlating this information, you may easily find out why specific query, for example, with ideal plan and no obvious weights reported by performance schema, why it still may be slow. The reason may be absolutely outside of MySQL, or it may be related to not yet detailed enough native MySQL instrumentation. Both cases happened in my practice, sure. So you get.
Do you like to share with us some stories?
You shouldn't forget everything that you did before, but you should start a new approach to a new look on the system from the operating system side, considering MySQL D as just one of the processes.
Do you like to share with us some interesting stories where you have combined everything, right, to get into the root cause of the bottleneck?
Definitely. There are a couple of stories. One of them is briefly presented in my talk. I will share the other one that happened probably even this year with MariaDB. There is a great MariaDB feature called thread pool. So it allows to scale to much larger number of connections, assuming that each connection is executing short running queries. So do not occupy the resource, the thread, for a long time. So with this feature, we had a customer who had a problem that sometimes they already switched to thread pool to scale, that in some cases in thread pool, even simple connections, simple statements start to take a lot of time to execute. Eventually, they could even report something to the error log, like we were not able to do something for the predefined times. So in MySQL 10.5, actually, after this incident, there are some insights added to not performance schema, to the information schema about the internals of thread pool working. But at that moment, it was clear that the problem is with the thread pool. There is some weight, but we could not see where is it. So I was discussing with a thread pool developer, and he told me, can you give me a stack trace at the moment when the problem happens, so I can see where is it in the thread pool? It's exactly the task for dynamic tracing. So as long as we agreed on what function to add a dynamic probe to, I've added the probe. I've told customer to install perf in that case because it was old enough Linux, and it was easier for me. So they installed perf, they've got root access to run it, they added the probe, and got a sample of stack traces during the problematic period. So immediately we got a sequence of calls in that trace that led to some weight in the thread pool. And it was absolutely clear for the developer from the first second of looking into that why that happened. And we added a feature, a dedicated listener thread per thread group or whatever, just 3.10.5 new feature documentation. All this story started with a quick and efficient way to find out what happens at the moment when it happens. And it was all due to dynamic tracing initially. Now we added native database tools for some insights and even some options to prevent the problem altogether. But it happened after. So this is how it works in practice, and it's really great. So now when people need something, they just ask me, in MariaDB, do you have a way to attach a probe or do something, do some magic to show me the stack trace when this or that happens? How to find out this or that stuff? They can do it in debugging sessions. Surely they are way more advanced people than me. But how to make it happen specifically in production at specific moment at customer side, when they do not use debug binaries, when we do not have a live debugging session because it's a production system, we may not get access. This is where dynamic tracing steps in and works really great. And it happens elsewhere as well. It was not invented in MariaDB, and there are developers who recently joined us who did it before. There is Brandon Gregg, whom I mentioned, who does that for decades, and like for last maybe 8 or so years since he's using Linux, adding and checking more advanced dynamic tracing tools just to be able to do this stuff at scale at the moment when it's needed. So I hope this story, it's a real one.
Interesting, very interesting. Yeah, it is very interesting. It's very interesting. All right. Thank you, Valerii. Thanks for giving detailed, rather high clarity to the entire ecosystem, like how you can combine the dynamic tracing utilities with the native tools and troubleshoot MySQL from a broader perspective than looking at, hey, you know something, I'm looking at MySQL MariaDB infrastructure looks good. I don't know, there is something else externally is impacting performance. But then when I combine BPF, dtrace, and native MariaDB MySQL tools, if I combine it, I'll have a clarity. There will not be any fog anywhere. Like, you know, I don't know, it's not happening here. So
so dynamic tracing is basically just an efficient implementation of the idea that you should approach the database server problems both internally from the code and from internal instrumentation and from the operating system where it eventually runs, and maybe even from the hardware side, because with dynamic tracing you have access to hardware counters as well. So this was proved efficient even in MySQL history to apply this approach. This is how it started to scale. We now can, thanks to dynamic tracing, make it like a commodity approach. So there is only one really serious big problem for any DBA. They need sysadmin level of access. They need root access, at least pseudo access to specific commands. So they have to cooperate with their system administrators, hardware guys, to be able to run this stuff. It may be hard from security point of view, it may take some time, it may require some negotiations and explanations, and actually what DBAs can do, they can just tell you, you know, sysadmin, please put it into your script, check how it works, this is the command I need, and just send me the output. I do not need even write. That's how I work. I do not work with customers in banks with remote login to their system. I'm not allowed even to enter the building ever, even if I would try. So, but I send instructions. I explain to people how it works. I show it. I speak about it at the conference. So they are not hesitating and they are not scared of doing these things. And Linux developers kindly tested that for us, so that it's a low impact tracing as much as possible. So thank you for them, for these new tools, and we should just be aware, and as long as we move to recent Linux's kernel 5s, we have all the plenty of tools for the job with different impact and with different capabilities. Please study that and use that. That's my message to the attendees and those who listen to my talk now.
So this is personally from me, right? It's very, very rare to meet somebody who is so passionate about educating the community, right? You've been a very active committer, you've been passionate about educating it. It's really a great privilege, Valerii, to having you in this conference, talking to you every time, reaching out to you every time. It's always a great experience because we get a clarity. Looking forward to a lot of support from you, Valerii, personally, as well as from a community standpoint of view. Wishing you a great holidays and Merry Christmas and 2021 in advance. So thanks again for talking in this conference.
Hope next year will be better, and this one was already great with online conferences. Your is just the recent example. It's good end of the year for me at least. It will be the last one for me. Thank you.
Thank you.